So we're gonna try and solve this question, number 9 from fall 2018. So it asks us to find the electric flux density field everywhere when we have volume charge density when rho is less than 1, and surface charge density when rho equals to 2. So to visualize this question, to have better understanding, we can always draw. So this is rho equals 1. This would be rho equals to 2. And the height would just be L. So in this case, our Gaussian surface could have 3 different cases. One is when the Gaussian surface, which has rho less than 1. And another one, when rho is bigger than 1 but smaller than 2. The last one, rho bigger than 2. Okay, so we're gonna try from the case 1. When rho is less than 1 and bigger than 0. So we all know the Gaussian law here. This equals to charge enclosed, and that is just volume charge density times volume differential. And in this case, we have cylinder. So D is in rho direction. In other words, D only has component in rho direction. So top and bottom part of the cylinder would be negligible since their integrals would be just 0. So we can always look at side only. So if you look at the right side of this equation, this just means charge inside of a cylinder, and charges in that cylinder are uniformly distributed. So it just becomes volume charge density times the volume of it. And also, to simplify the left side, D is in rho direction, as I said, so we can always write this like this. And this value just gives us ds in rho direction. And again, Q is uniformly distributed. The flux for this cylinder would just be D times area of side. And this equation would work for the 3 of the cases. So when rho is less than 1, here height L could be raised, pi could be raised, and it reduced to 1. And in the end, we have volume charge density times rho divided by 2. And the volume charge density is given by the question right here. It equals to 2. So it cancels each other. It becomes rho. So this is our first case. And second case, when rho is bigger than 1 and less than 2. As I said, we can always use this equation for this problem. In this case, the only difference that is in here is rho is actually bigger than the first cylinder here. So the charges that are inside of the cylinder is fixed, right? So we can just write it down as, because rho is equals to 1, rho equals to 1. Here we go. Sorry. So in this case as well, L cancels each other. Pi could be erased. So V equals to volume charge density divided by 2 rho. We know the volume charge density, it is equals to 2. So it's 1 over rho. The last case, when rho is bigger than 2, we need to consider 2 components for this, because we already have, when we look at rho is bigger than 2, there's charge. There's already a charge inside of that boundary, this one. And we also have a surface charge density when rho equals to 2, right here. So in this case, this equation would be we have to include this one as well. Plus surface charge density and the area of it. You just put the numbers in. 2 pi L plus the surface charge density is right there. It's -2. -2. 2 pi. In this case, rho equals to 2. So 2. So L cancels each other. Pi cancels each other. It becomes 2 plus -8, which would be -6. So D equals to -6 divided by 2 rho. And this becomes -3 divided by rho. We can always put the values together. So when D equals to rho, when rho is less than 1 over rho, when rho is bigger than 2, bigger than 1, and less than 2. And finally, -3 over rho when rho is bigger than 2. Thank you.